Kia ora and welcome to this video on question 6 of the 2013 School Calc exam. Emphasising question 6 because it's been a while since there's been 6 questions. If you watched question 1 of this year, you would have seen that whilst there were 6 questions, you could choose any 5. So the first part of this is a problem, very common problem involving complex numbers and trig identities. I think I've recorded a video very similar before. Part B, a system of linear equations with a bit of context to it, and it's quite an easy problem if you notice the trick. And then the alternative problem is another complex numbers problem involving ellipses, and it's a little bit trickier unless you're good with geometry. Okay, part A. We need to prove these trig identities by considering the expansion of cis theta to the power of 5. It says or otherwise, but we're just going to look at the expansion because it is definitely the easiest way to go about proving these trig identities. Cos theta plus I sine theta to the power of 5. There are two ways of expanding it. One of the ways is using the theorem, de Moivre's theorem, because when we take a complex number and raise it to the power, notice that the modulus is 1. It's not r cis theta, it's 1 cis theta. So we don't have any numbers there in front of the cos or the sine. We usually power the modulus, but 1 to the power of 5 is 1. We multiply the argument by 5. So we end up getting cos 5 theta plus I sine 5 theta. Okay, so that's using our theorem, which says r cis theta to the power of n is r to the n cis n theta. But I said r was 1 and n is 5. Okay, so that should make it quite clear how to prove these trig identities, because cos 5 theta has appeared as the real part and sine 5 theta has appeared as the imaginary part. Okay, there's a different way of expanding this. Of course, you could use a binomial expansion. Using the binomial theorem involves Pascal's triangle. We're essentially expanding a plus b all to the power of 5. The binomial coefficients for an expansion with 5 in it, you can find them on the formula sheet. Where there's Pascal's triangle there, you look at the 5th row, it goes 1, 5, 10, 10, 5, 1. So 1, 5, 10, 10, 5, 1. A plus b all to the 5. You'd start off with a to the 5 there, a to the 4, a cubed, a squared, a, and then a to the 0 is 1. And then on the other side, you'd go b to the 5, b to the 4, b cubed, b squared, b, and then b to the 0. Put some pluses in. Okay, so that's how we expand a binomial really quickly. And so we do the same thing for the trig expressions, where a is cos theta and b is sine theta. Actually, no, sorry, b is I sine theta. So expanding, we've got cos to the 5 theta plus 5 cos to the 4 theta times I sine theta to the 1 plus 10 cos cubed theta I sine theta squared plus 10 cos squared theta I sine cubed plus 5 cos theta I sine to the 4 plus I sine to the 5. Some of these terms are real and some of them are imaginary. The real terms in yellow, cos to the 5 theta. This term is real because there's an I squared in there, and I squared is negative 1. This term is also real because I to the 4 is just 1. So if we equate those, cos to the 5 theta, the real part of the expansion, must equal cos to the 5 theta plus, so it's going to be a minus because there's an I squared, minus 10 cos cubed theta sine squared, and then the last term I to the 4 is just 1, so we get plus 5 cos theta sine of the 4. Okay, that's equating real parts. And then equating imaginary parts in a similar way. Sine 5 theta is going to be this dude here. I don't need to take the I with us. It's just the coefficient in front of I. Okay, those three terms there. I've got to be careful though, because I cubed is negative I, and I to the 5 is positive I. Remember that powers of I repeat every 4. So I've got sine 5 theta is equal to 5 cos to the 4 sine minus 10 cos squared sine cubed. The fact that I cubed has a negative as negative I, and then plus sine to the 5. Okay, have we done it? I believe we have. Let's have a look. Cos to the 5 theta minus 10 cos cubed sine squared plus 5 cos sine to the 4. And the other one's correct as well. We don't, normally when we prove these, we would get rid of one of the trig expressions. You see how we've got cosines and sines, but if we turned the sine squared into 1 minus cos squared, and we did that there as 1 minus cos squared all squared, then we could eliminate all the sine stuff and just have a polynomial with cosines in it. But the question here didn't require us to do that. We've actually already answered. So let's go with a box and a smiley face. Okay, part B. The first option, as I was saying, is the easier of the two options. A teacher sets 99 homework questions for a calculus class each week of 3 different types: easy, difficult, and impossible. The number of questions of each type given in week N are represented by X, N, Y, and Z. So it's a recursive formula. The teacher decides the questions for the next week based on a combination of the questions set in the previous week, which kind of makes sense. You know, if you, as a teacher, if you've given too many easy questions in the previous week, you might change it up for the next week. But this teacher's gone next level and actually come up with some sort of formula. Her class noticed that the number of questions of each type stabilizes after several weeks. Good on them for noticing that. That is, in the long run, they notice that the number of questions of each type is equal at n plus 1 and n. That's the whole stabilizing thing. How many questions of each type will the teacher give each week? So I'm going to assume here that you've got a graphics calculator that enables you to solve this problem. We're going to change the x to the n plus 1 to x to the n, y to the n, and z to the n, because we're looking for the stable solution. And then I'm going to drop the subscript notation altogether. So I'm going to solve x equals 0.8x plus 0.7y plus 0.6z. That's one equation. Y equals 0.1x plus 0.2y plus 0.4z, and z is 0.1x plus 0.1y. If you solve these manually, you'd have to substitute one equation into the other or eliminate the variables. But it's a linear system of equations, so we can just go into our graphics calculator. Under equation, go to simultaneous, 3 unknowns. The only thing that we need to do is move the x, y, and z to the other side. So the left-hand side will be 0, 0, 0, and this will be minus 0.2x. This one will be minus 0.8y, and the z one will be minus z. Okay, so rearranging that, the coefficients are a bit different. So if we do that, type in all the coefficients, or use matrices if you're familiar with them. It gives you a maths error, and it turns out that the system here is dependent. This system is dependent and has an infinite number of solutions. And so normally in that case, if you did the NCA internal assessment, you'd have to find a general solution. But the question is saying how many questions of each type. So it suggests that it can be answered. And the reason why the system is dependent is that one equation can be just formed from a combination of others. But we haven't used the extra piece of information in the problem, which is the teacher setting 99 homework questions every week. So if we add in a fourth equation, giving us a bit more information to solve it, x plus y plus z equals 99, you can drop off any of the three equations that you want. You'll get the same answer regardless. So if I get rid of the third equation and replace it, 1x, 1y, 1z, 99, it enables you to solve it. Solving on the GC gives 76, 14, and 9. 76 easy, 14 difficult, and 9 impossible. And that's a long-term solution. So originally that wasn't what was happening, but it got to a point where the recursive sequence started generating the same every week when x to the n became x to the n plus 1, and that was the solution that the students must have noticed. Okay, the last part tells you to use your knowledge of ellipses, so it's suggesting you must do this geometrically, otherwise it's just going to be really, really difficult. If you sub an x plus iy in here, you're going to have to square stuff. You're going to end up with a really horrendous equation. What you need to realize when you're dealing with something of this nature, and I'm going to start with an easier example just to explain this. So if I had z plus I in modulus plus z minus I equals 4, for example. I'm just dealing with equals at the moment, then we'll deal with the inequality and the fact it's a double inequality. The locus of this is an ellipse. The ellipse has foci at I and negative I. And this dude here is equal to 2a. You need to know what a stands for in an ellipse. We'll talk about that in a sec. And that's the sum of the distances from z to the foci. So what that will give us is an ellipse that it's a terrible ellipse. Just be a little bit, that will have to do. And this will be at 2i, the vertex will be at 2i, negative 2i. Okay, now the reason why that would be the answer to the question is because if I take any point on an ellipse, so any point z, if I go there for example, the distance from one focal point to the point on the ellipse plus the distance from the other focal point to the point on the ellipse, if I call that L1 and L2, L1 plus L2 always equals 2a on an ellipse. Okay, that is the special geometric property of an ellipse. And so I could pick, for example, the z value right down the bottom here at minus 2i. The distance from one focal point to that, well, that's actually 1, and the distance from the other focal point is 3, and 1 plus 3 is 4. So that's how I knew where the vertices were. I knew to put the vertices at 2i and negative 2i, which is a diameter of 4. In general, when you have an ellipse, if it's horizontal, then this is A, distance from the center to the vertex on the major axis. If it's a vertical ellipse where the foci are on the y-axis, then that will be A. Okay, so if you're not sure about conics and you haven't seen that sort of thing before, then play around on Desmos and have a look at different equations of ellipses. But how did I know it was an ellipse to begin with? Okay, the way I read something like this, or actually let's do the second one, it's better. The way I read the modulus of z minus I, geometrically, I read it as the distance between z and I. Okay, and the reason for that, I think I covered this in another video, but if you haven't seen it, if we take the point I here and a point z there, the distance between z and I is this length here. But it's also this distance. And this complex number is z minus I. Because when you take away I from a complex number, you move it down by 1. And the distance of a complex number from its origin is the modulus. So this distance, z minus I, is just the modulus of that complex number, which is equal length to the distance between z and I. So when I see that expression in green that's in the equation highlighted there, I read that as the distance between z and I. And the other one, the first one, which I highlight here in yellow, is the distance between z and minus I. And because the sum of those distances is a constant, and I just made that constant 4, I put foci in at I and minus I, and I use the property of an ellipse where the sum of the two distances from the ellipse to the focal points is a constant, to get the major axis having a length of 4. Because this foci are equally spaced, one's one above the origin and the other's one below the origin, the center of my ellipse is the origin. Now if I did this algebraically, and I wanted to find the equation of this ellipse, I would have to sub in x plus iy. So let's just see how many lines of algebra this is going to do. It's going to do our hidden, I'd say skip to the end of the video right now. It's x plus iy minus I equals 4. I don't know if your teachers ever derived the equation of an ellipse before, but I'm going to give it a go with this one. You'd group the real and imaginary parts together. We take the modulus, which is the real part squared, the imaginary part squared, square rooted. And we want to square both sides of this. The convention when you've got a double square root is usually to move one to the other side first. It makes it a little bit easier. Oopsies. Square both sides. So I'm squaring the whole of the left hand side, not the individual terms. So it's going to square the whole of the right hand side. 4 squared 16, 2 lots of the middle terms, and then the last term squared. Oopsies, which will mean I'll get rid of the square root. X squareds cancel. So do the y squareds that are in both of those quadratics. Y squared plus 2y plus 1. Y squared minus 2y plus 1. You can cancel off the 1's and the y squareds. Move the minus 2y to the left hand side. 4y minus 16 equals negative 8. I'm preparing to square again. And this is just for one of the ellipses, right? The problem had an infinite number of ellipses to be to satisfy the inequality. Divide everything by 4. Square both sides again. I'm squaring the whole of the left hand side and the whole of the right hand side. Y squared minus 16, no, minus 8. Y plus 16 equals 4. X squared plus y squared minus 2y plus 1. 4x squared, 3y squared if I join the y squareds on the right hand side, minus 8y terms cancel. It's one on both sides, and then we've got equals 16 minus 4 is 12. Divide everything through by 4. No, by 12, sorry. 1 equals x squared over 3 plus y squared over 4. Now, this equation is written in the format x squared over b squared plus y squared over a squared equals 1. It just so happens that I chose a to be 2, so 2 squared is the same as the 2 squared is equal to 4, which is the major axis. But I could have got that straight from my picture and gone, okay, the centre, there's no brackets in the equation because the centre is the origin. The semi-major axis is the distance from the centre to the vertex, which is the length 2. Okay, it's 2 from the centre to the top. So I would have gone x squared over b squared plus y squared over 4 equals 1. And then to find the b, I would have used the fact that the vertex, not the vertex, the focus, need another colour. The focus, which is normally given the letter C, from the centre to the focus is 1. So I've got C is equal to 1, and there's an equation that links A, B, and C together. It's on the formula sheet for an ellipse. Let me just find it. It is B squared equals A squared minus C squared. Now we know what A squared is, it's 4. And we know that C is 1, so C squared is that. So B squared is 3. And therefore x squared over 3 plus y squared over 4 equals 1. And that's the equation straight out of the picture, as opposed to deriving it using algebra. Where does this b squared equals a squared minus c squared formula come from? If you have an ellipse where this dude is C, if I draw a triangle there, this would have to be A, and that would also have to be A. Remember, the sum of the distances is 2A, but if I draw an isosceles triangle, it has to split in half. And then this is B, the distance from the centre to the top, and I use Pythagoras on that right angle triangle there. B squared plus C squared equals A squared. If I turn the ellipse around and it's vertical, then my A and my B switch around. Okay, let's actually solve the problem now. We've got this equation is related to an ellipse, the sum of two distances being a constant. Now we can consider this inequality. There's some special cases though which actually make this quite a tricky problem. But the first thing I'll do is put in those focal points. So we've got I there and negative I there. If k is less than 1, there are no answers that solve this problem. K is less than 1. Because what that would say is that the distance, remember that k is positive, but what that would say for this inequality is that the sum of the two distances, this yellow distance here, the distance between z and minus I, and the distance here between z and I, has got to be greater than or equal to 1, but less than or equal to 2. But there's just no z values that's the case, because the distance between negative I and I is already equal to 2. So if I go, oh, could z be there? The distance between z and I and the distance between z and minus I, if I add those up, it's got to be greater than the distance between I and minus I, which is 2. So that's not possible. There's just no z values that will work. So there's no solutions for that. If k is equal to 1, then our inequality becomes the sum of those two distances, the yellow and the green distances, has got to be between 1 and 2. Okay, well, it's always going to be bigger than 1. We know that. But less than equal to 2, how could the distance be less than equal to 2? It could be equal to 2. Any point z, actually I'm going to draw this in a different colour. If k is equal to 1, any point z that is on this axis, a purely imaginary number, between I and minus I, the distance from z to I, which will be this green bit, and the distance from z to minus I, which will be this distance, that will always be equal to 2. It can't be less than 2, but it would be equal to 2. So k equals 1 is a special case where the solutions to it, z is a purely imaginary number on the y-axis between negative I and I. Now, if k is anywhere between 1 and 2, that's our next special case. K, if k equals 1 is a special case, but if k is bigger than 1, but less than or equal to 2, now we considered k is equal to 2 earlier, because when I made k equals 2, the right hand side here became 4, and so we already know what that ellipse looks like if that thing's equal to 4. And I'm going to draw that one. Okay, this would be if k is equal to 2. If k is somewhere between 1 and 2, then we get an ellipse inside there, which has focal points at I and minus I. And remember, the reason for that is if we take z somewhere here, the distance between z and I plus the distance from z to minus I is always a constant. So any value of k between 1 and 2, not including 1, but could include 2, is going to describe the set of points inside this ellipse. Okay, so any point z that's inside that ellipse, so for example, this point, the distance from z to I plus the distance from z to minus I, the sum of those two distances is going to be equal to an ellipse that has a major axis equal to the sum of those distances. So between 1 and 2 we get a solid ellipse. Foci minus I and I. When k gets bigger than 2, it gets a bit strange, so I'm going to draw that as a separate graph. When k is bigger than 2, again we still have our focal points at I and minus I, but now our equation's a little bit different. We've got as an example, the marking schedule looks at k equals 3 as e.g. k equals 3. So we'll do that. So if k is 3, then the inequality becomes 3 less than equal to z plus I plus z minus I less than equal to 6. So our ellipse, the major axis has to be somewhere between 3 and 6 in length. Because remember that these dudes here, this is equal to 2a for the ellipse. So the distance from I plus the distance from negative I, those have to add to be a number that's between 3 and 6. The major axis has to be somewhere between 3 and 6 long. Now, if I draw that with a major axis of 3 long, it's going to look like this. Okay, that has a major axis of 3. And then the other alternative is a major axis that's 6 long, which is going to be this big. Come on, good ellipse, come on, good ellipse. Yeah, that will do. So that one's got a major axis of 6. And any z value that is in that region, so the answer is actually kind of like a squashed donut, a region between two ellipses. If I pick a value z, say, inside that region, the distance from z to I plus the distance from z to minus I, when we add those distances, we're going to get a number that lies somewhere between 3 and 6, because that is a particular ellipse that has a major axis between the numbers of 3 and 6. Okay, so if k is greater than 2, we get a region between two ellipses. One with a major axis of k, and the other a major axis of 2k. Yeah, I think the systems of equations question was a lot easier, and I'd imagine that most of the students in that year would have done that. Anyways, I hope you found that video useful. The last question, that ellipsis one, I forgot to mention, it is very similar to one of the question 5 problems in the 2021 paper, which if you did it algebraically with the x plus iy thing, it just blew up and wasn't easy to work. I'm talking about question 5C of 2021. So if you haven't seen that video, maybe pop in and watch that now. All the best.